Welcome back, everybody. In today's video, we get to finally talk about derivatives, which is one of these major concepts in calculus that we're going to talk a whole lot about. So, what is a derivative? Well, in our previous video, we talked about how to find rates of change, right? Specifically, an average rate of change. Well, what a derivative is an instantaneous rate of change at a specific x value. Okay, so what do I mean by that? Well, remember, we had this nice little formula for average rate of change where we found the difference between my y values or my output values. So I'm going to write it like this, function notation. It's this difference between your output values divided by, divided by the difference between your x values. So this was my average rate of change formula. And we used that, so if I use the same example that we used in the previous video with the unemployment rate, we use that to connect 2 points and decide, okay, on average, this is what's happening to the unemployment rate. It's going down by about, what was it, like 0.5% each year? Something like that, right? Where we said, on average, this is how the unemployment rate is changing over this interval of time. Well, what a derivative does is it says, well, what about in 2008? What about at a very specific time? How is the unemployment rate changing in 2008? Well, we can see that obviously, right, the unemployment rate's increasing. It's going up, which is not the same as what we found in the average rate of change. So we could potentially have a very different value if we focus in on just a specific point. What's my instantaneous rate of change at a specific point? So that's an important thing to keep in mind with derivatives, is with the derivative, you're only working with a single point. We only have 1 point to work with. Well, in that case, how do we calculate an instantaneous rate of change if we only have 1 point? If I try to use my average rate of change formula, but I only have 1 point to work with, what am I going to end up with? I just end up with 0 over 0, which is indeterminate and does not help us at all. Well, the way we're going to do this is we're going to use limits. We're going to take my average rate of change formula, and I'm going to change this up slightly, where A represents the point that we're looking at, the single point that we're looking at, and we're going to find a rate of change starting at A, but we're going to let X get really, really, really close to A. How do we do that? We use a limit. We're going to let X get infinitely close to A. What does that look like? So if I come back to this example, what that means is I'm going to pick points and make rates of change starting from the point that I'm concerned about, and then picking points getting closer and closer. That one wasn't the best straight line. Getting closer and closer to my actual point, right? I let these x values get closer and closer to the point that I'm concerned about. And as I do that, then the line that I create is more accurately represents what's happening at that specific point. So we use limits to calculate a derivative. So another way you'll see this done with derivatives is using something called the difference quotient. So the difference quotient looks something like this. I did that wrong. So the difference quotient looks something like this, where once again, A represents the x value that I'm looking at. So this is at a specific x equals A. So if we were talking on unemployment rate, my x value would be 2008, right? It's the point that we're looking at. And then I use this formula. Well, where does this formula come from? Well, this formula it's it's just another version of the rate of change formula, where h represents your change in x values. It's your change in x, or your delta x. And so it'll calculate the same thing. If we want to find an instantaneous rate of change, what do we want to be true about h? We want h to get infinitely close to 0. So both of these are how I can actually calculate a derivative. We consider these my limit definitions of a derivative. This first one comes directly from my average rate of change formula, right? And the second one, like I said, is using something called the difference quotient. So this is using the difference quotient. Well, let's look at an example here. So consider this function. We've got f of x is equal to 4x minus 3x squared. I have the graph right here. So this is my graph of f of x. And I want to find the derivative at x equals 2. So notice how I only give you a single point because we're talking about an instantaneous rate of change. I want to find the rate of change at this specific point. So let's find this point on my graph. That's right here. What is my graph doing here? What is my slope approximately here, right? That's what we're talking about. We're talking about a rate of change. Well, if I just kind of eyeball it, it should be negative, right? Should be fairly steep because my graph is decreasing at this point, right? My graph is going down, so I should expect to see some sort of negative value. But let's use one of my limit definitions to actually try and come up with this derivative, okay? I'm going to use the difference quotient, and you'll notice that I prefer the difference quotient. I'm going to use this frequently throughout this chapter 1 and chapter 2. Well, just chapter 1. You're welcome to try it using the other form, but I'm going to use the difference quotient. So if I use the difference quotient, I'm going to take the limit as h approaches 0 of, well, f of a plus h. What is a in my case? A is the x value the specific x value that I'm looking at. So that means I'm going to do f of 2 plus h minus f of a, which is just f of 2, all over h. F of 2 is simple enough, right? F of 2, that just involves me plugging in 2 to my function. But what about f of 2 plus h? Well, that just involves plugging 2 plus h into my function wherever I see an x. So wherever I see an x in my function, I'm plugging in 2 plus h. And then, like I said, f of 2 is just me plugging 2 into my function. So let's simplify this a bit and see what happens. Notice I'm not even trying to plug in 0 because I know, because if I do that, I'm just going to get 0 over 0. You're welcome to try it. Plug in 0 right now and see what happens. If I do it, I'm just going to get 0 over 0. So I got some more work to do here. So let me go ahead and distribute and try and simplify this numerator. So I'm going to distribute here, and then I need to also do 2 plus h squared. So I'm going to be left with 8 plus 4h minus 2 plus h squared gives me 4 plus 4h plus h squared. You're welcome to, if you're not sure how I got that, you're welcome to just work that out on the side. Minus, well, what do I get in here? 4 times 2 is 8 minus 3 times 2 squared. That's 3 times 4, so 8 minus 12. Well, let's keep simplifying. I get 8 plus 4h minus 12 minus 12h minus 3h squared minus 8. And now I'm going to distribute this negative to both terms. So minus 8 plus 12. Well, notice, what do you notice so far? I have a positive 8 and a negative 8. They add to equal 0. I also have a negative 12 and a positive 12. They add to equal 0. So you'll notice that the terms that don't have an h in it cancel out. They end up going to 0. What does that leave me with? That leaves me with the limit as h approaches 0 of 4h minus 12h minus 3h squared all over h. I've got some like terms there. So this is equal to the limit as h approaches 0 of negative 8h minus 3h squared over h. But you'll notice that both of the terms in the numerator now both include an h. So I can factor out an h. And I'm left with h times negative 8 minus 3h all over h. The h in the numerator cancels with the h in the denominator. And I'm left with the limit as h approaches 0 of just negative 8 minus 3h. So I've done a good amount of work of expanding that numerator, consolidating it, combining like terms, canceling out things that add to 0, factoring out an h, canceling out the h, and by canceling out this h, I've now eliminated what was causing the discontinuity, and I can now plug in 0 for h. And so I'm now left with negative 8 minus negative 8 minus 3 times 0, which is just negative 8. So, despite only having 1 point, we were able to come up with a rate of change at that point. We now know what the rate of change is at the point at this point right here on my function. It's going down 8 and over 1. Remember, this is a rate of change, which means I can effectively think about it as a slope. I'm going down 8 over 1, negative 8 over 1. Take a look at this graph right below it. This is me zooming in on that point. So right here is the same point at 2, negative 4. That's what this point is, 2, negative 4. This is the same point. But I've zoomed so far in that this line looks linear, right? I've zoomed so far in that this line looks linear. And if I zoom in any more where I can actually see the grid lines, let me make that dot a little smaller. Then if you notice, I'm going down 1, 2, 3, 4, 5, 6, 7, 8, and over 1. So sure enough, this answer that I got by using limits and calculating a rate of change using limits matches what the graph is actually doing at this point. I'm going down 8 and over 1. So, using limits, we were able to come up with the instantaneous rate of change for this function at a single point. We were able to find the derivative, which is, that's what a derivative is, right? It's an instantaneous rate of change. So one reason why we like having derivatives is derivatives help us calculate the tangent line of an equation. So what is a tangent line? A tangent line is a linear approximation of a function at a specific point. It's pretty much saying, like, if we have a function and we pick a specific point and say, okay, let's pretend that the function turns linear here, then that's what the tangent line will be. It's our approximation of what the function would be if it were linear. So visually what this looks like for this function right here is if I took that point and drew a roughly linear line there that matches what the function's doing. So notice how I draw it kind of alongside the function. If I change this and drew it like this, yeah, that's linear, but it doesn't approximate what the function's actually doing. So that doesn't count as a tangent line. Instead, the tangent line is that green line where it's approximating what the function's doing. Well, guess what the slope of that tangent line is? It's negative 8 over 1, right? That's pretty much what we did here. This is a tangent line. We zoomed in so far that it's effectively linear, it looks linear, that's what the tangent line is. It's a tangent line approximation. It's a linear approximation of what the function is doing. So once again, how do how do derivatives relate to this? The derivative is the slope of the tangent line. So let's say, here's my tangent line, approximate. This is me just hand drawing it. But here's my tangent line for the function at this point 2, -4. Could I come up with an equation for this? I totally can. And, we're used to seeing equations in this form, y = mx + b, but for tangent lines, it's actually more helpful to use what's called point slope form. Point slope form looks like this. Y minus your y value equals m times x minus your x value. We like using point slope form for tangent lines because to use slope intercept form, you have to know the y-intercept. And a lot of times when we're making tangent lines, we're not making them at the y-intercept. So we don't know the y-intercept, but we should know one of the points that I go through. So if I use this point slope form, let's see if we could find the equation for this specific tangent line. I'm going to have y minus, what's my y value for this point? For that, I can come look at my coordinate point. My y value is just -4. So I'm going to have y minus -4 equals, what's my slope? Well, that comes back to what I just said here. My slope of the tangent line is the derivative. It's what we found as the derivative. It's the derivative of the function at the point. So in our case, that is -8. And then I'm going to have x minus my x value for the point, which was just 2. And I have my tangent line equation. I could, of course, clean this up a little bit, right? Y minus a -4 is just y plus 4. If I want, I could distribute this -8 to both terms. And if I take it one more step, yeah, I can get this into slope-intercept form by just subtracting 4 on both sides. So we can eventually get into slope-intercept form, but it's really nice to start using point-slope form. But this represents my tangent line equation. If I go and graph this line, it's going to exactly match this linear line that I have right here in my zoomed in graph. It's going to exactly match that because it's approximating the function as if it were linear. Next, let's talk differentiability. Let's make sure I spell this right. Differentiability. Okay, what am I talking about with differentiability? Differentiability is just asking the question, can I find a derivative at a specific point? Well, this really just boils down to a good way you can think about this is, can I draw a tangent line? Well, let's look at this example. Let's start with this example here. So I've got a function going wah, 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 and let's pick this point. Is the function differentiable at this point? AKA, or another way to think about it, right, is can I draw a tangent line here? Well, can I draw a linear line that generally approximates that function? I absolutely can. In fact, if I pick any point on this line, I can draw a linear line that roughly approximates the function. So every point on this line is differentiable. Why? Because you'll notice this is a smooth, continuous function. So as long as my function is smooth and continuous, you can take the derivative. You can take the derivative. What do I mean by smooth? Well, take a look at this example. So here I have a function that kind of looks like an absolute value function, right? Where you've got this kind of V shape. And let's pick this point. Is the function differentiable at this point? So this would not be considered a smooth function because you have this angle in your function where you have this sharp turn. Can I draw a tangent line there? Well, I could draw one like this. I could draw one like this. I could draw one like this. There's an infinite number of ways I could draw a tangent line here. And so because of that, I really can't find a derivative at this point. My function is not differentiable at that point. No, yeah, if I pick a different point, I'm differentiable there, right? Because at that point I'm smooth and continuous. It's just not differentiable at that corner. What if I have a spot on my graph where I'm not continuous? What if I have a jump? Can I draw a tangent line if I have a jump? Absolutely not. So if I specify like this x value, can I draw a tangent line if I've got two different possible x values that I'm working with? No. So if the function is not continuous at a specific point, then it's not differentiable either. So in order for a function to be differentiable, it has to be continuous. So the last thing we need to talk about with derivatives is, do I have to specify the x value for a derivative? Let's go to my limit definition of a derivative again. And once again, specifically, I'm going to look at the difference quotient. F of a plus h minus f of a all over h, where a represented my x value that I specified, right? Because I'm looking at a rate of change at a specific point, an instantaneous rate of change. But what if I don't specify an x value? Well, what that really just means is instead of having a plus h, I'm going to put this back to just x, where x is variable. I can change x. I can choose x to be whatever I want. Can I still calculate this limit even if I don't know what x is? Well, let's try it out. Let's go back to that same example where my function is equal to 4x minus 3x squared. So let's try it with this function right here. So with that function in mind, when I plug it into the difference quotient, it's going to look kind of similar, right? Everywhere I see an x, I'm going to plug in x plus h for this first part. And for the second part, I just plug in x for x. And so I'm just left with my function, right? I'm just left with f of x, which is 4x minus 3x squared. And that's all over h. So just to kind of keep us organized here, this piece right here is your f of x plus h. And then this is your f of x. Everybody okay with that? So what do I do from here? Once again, if I try and plug in 0 for h, I'm just going to get 0 over 0. I'm going to get something that's indeterminate. So I have to do something more. Let's go ahead and expand this. And then we can try simplifying. So let's expand this. I'm going to get 4x plus 4h minus 3 times, if I do x plus h squared, I get x squared plus 2xh plus h squared. Minus, let me go ahead and distribute that negative sign. I'm going to distribute that negative sign to both terms. And so I get minus 4x plus 3x squared. Well, let's keep going. 4x plus 4h. I'll distribute that negative 3 to all three of these terms. And I'm left with negative 3x squared minus 6xh minus 3h squared minus 4x plus 3x squared all over h. Well, now what? Well, a similar thing happens to what happened when I was doing the difference quotient before. I have a 4x, I have a negative 4x. Those will subtract equal 0. I have a negative 3x squared and I have a positive 3x squared. Those are going to add together to equal 0. What does that leave me with? That leaves me with a bunch of terms that all have an h in it. Right? I have 3 terms that all have an h in it, which means I can factor that h out. I can factor that h out of the numerator. And that leaves me with 4 minus 6x minus 3h. That h that I factored out now cancels out with the h that's in my denominator, and I've eliminated my discontinuity. So That leaves me with this limit as h approaches 0 of 4 minus 6x minus 3h. Now I can plug in 0, right? I don't have h in the denominator anymore. I can go ahead and plug in h equals 0, and I'm left with 4 minus 6x. Interesting. So I'm able to come up with a result, even if I don't specify an x value. I'm still able to come up with a result. What does this result represent? Well, this right here is what's called the derivative function. And we actually have a notation for this. So since my original function was f of x, my notation for this is f prime of x. So that's my notation for a derivative function. So that's one way to notate derivative functions. Another way to notate a derivative function is dy over dx. This also represents a derivative function. This represents a derivative of y in terms of x, but it's your derivative function. Okay, so these are the same thing. It's just different notations, but it represents my derivative function. What does a derivative function do for us? Well, what this does for us is now I can pick any x value I want. And instead of going through this whole limit definition process, I can just plug the x value into the derivative function in order to find the derivative at that point. So for example, I could plug in positive 1. And what does that tell me? That tells me that at positive 1, the slope of my function is negative 2. So my function is decreasing approximately this rate, down 2 over 1. That's what's happening at that x value of 1. I didn't have to go through the limit definition again. I used the derivative function to figure out what the derivative was at this new x value. Go ahead and get started on the homework. Good luck with it. I will go through a couple of questions from the homework just in my examples video. But if you have other questions, please reach out and let me know. Thanks.